Okay, and just so everybody knows, I started recording the meeting. Most systems I'm used to give you an announcement about that, but I'll make the announcement. So everybody, I wanted to introduce Lukas van Ginneken. I don't think he needs an introduction, but for those who don't know, he got his PhD in electrical engineering from Eindhoven University of Technology. He's been a technical leader, research staff member at IBM, technical leader at Synopsys, and the chief architect at Magma. And he's here today to talk to us about various issues in regression testing and quality assurance. So I'll hand it to you, Lukas.
Okay, thank you, Tom. I prepared some slides for related to regression testing and testing in general and quality assurance in the release process. And so I just wanted to quickly cover the outline of this presentation. So quality assurance and regression testing have to be seen in a context of the release process. So you verify that your releases, different states in the release, meet a certain quality threshold. And so first, I just wanted to go over the release process and what the roles are of the different participants in the release process. Then I wanted to cover a little bit about other types of testing, not just regression testing, and then move on to regression testing, and more particularly regression testing of the of optimization and some of the issues that you have to deal with in those regression tests, such as stability and repeatability. Please, at any time, feel free to interrupt with questions. This is merely a representation of my opinions and experiences in with this with regression testing. And so, if there are questions or suggestions, please let me know. So in commercial EDA, and my experience is mostly based on Magma and to a lesser extent on Synopsys and IBM, you can kind of roughly distinguish alpha testing, which is in-house testing, and beta testing, which is testing at the customer side. So alpha testing, we can distinguish different roles, such as the developers, application engineers, and quality assurance department. And beta testing can distinguish also different roles of the EDA department and the actual users, the end users, the designers. So I'll go back to these roles in a little bit. So in commercial EDA, you can kind of think of development process as a pipeline stretching from the developer who writes the code to the designer who is the user of the EDA tools and who is the target of the tools. So the tool, the code progresses to a number of stages in this release process, and the first stage is the quality assurance department who does regression testing. That's the main task of the quality assurance. Do regression testing and create releases. And when a regression fails, it usually goes back to the developer who has to come up with a fix for that regression failure. Then it moves on to applications engineering, who are the actual interface to the client. The client being a design house like Qualcomm or Texas Instruments or some sort of company like that that designs ASICs typically. And inside this client company, there is usually a support organization, an EDA department that supports EDA tools, that takes care of integration of EDA tools and does acceptance tests and things like that. So there are multiple stages, and they support the designer. So are there any questions up to this point? Okay. So the QA department is the main department that runs regression tests, and typically the QA department is the only department that's authorized to check in code on the main branch. And developers are not allowed to do that, and that's to protect the main branch against, introduction of new bugs. They determine the order of merges into the main branch and execute the release schedule. And they mostly run regression tests, but don't develop regression tests. Regression tests are usually developed by developers or applications engineers. So developers develop unit tests, usually for the part of the code that they're responsible for. They may introduce test cases, install test cases as regression tests that were originally submitted as test cases for bugs, for bug reports. And often the developer will also run regression tests before submitting a development branch for integration into the main branch. Applications engineering has the role of supporting customers. They are usually the interface between customers and developers. So usually customers do not have access to R&D immediately, but have to go through applications engineering to report problems or get support with issues and file bug reports. So applications engineering will file bug reports into the bug tracking system. That's usually not something that's done by customers, but by applications engineers. They receive or create test cases for bug reports. And they often also create end-to-end regression tests. And these are mostly previous benchmarks from competitive engagements with customers that are usually challenging designs that are, if successful, installed as a regression test. Typically, application engineering will not run regression tests. And then there are the customers who supply designs, libraries, floor plans, test cases of all kinds. And usually customers also develop their own acceptance tests so that they can do a regression test of their own when they receive new code before they roll it out. That's usually done by the customer's EDA department before they roll it out to their designers. Usually the QA department determines what features or what submissions from R&D will be merged into the master branch at a time. And some companies, I'm thinking mostly of Synopsys, are very organized about this process. So they have what they call a train schedule that is very strict and has a calendar of dates at which point new features or bug fixes or things like that are merged into the master branch, and so that a release can be released on time. You know, there may be a schedule that stretches a couple of months, and a particular feature or a particular module may only be merged in on a particular date or a couple of dates. Like there's 3 days or so, 5-day space on which they can integrate their stuff. Do they miss that date? Then that usually means they missed the release. So that's Synopsys installed this method, very strict and very organized and scheduled method to manage the large number of contributions that went into the release. So in the release process, there are a number of gates, basically points at which the process can be stopped. And those points are usually based on regression testing. So the first point of that is by the developer. The developer has to make sure that their branch is ready to be merged into the main branch. So if it's a bug fix, it would make sense to make sure that the bug is actually fixed and that the test case that was supplied with the bug report now works. Now, this test case can be installed as a regression test. That did not always happen, but sometimes that happened. But also, the developer has to make sure that his changes did not break anything else. So it's often necessary for the developer to run at least some of the regression tests to make sure that the bug fix didn't introduce a different problem. For bug fixes, that's usually not a problem. For new features, that is often a problem, as they can create instability in the system and break a number of things. So then there is, oops, I'll back up for a sec. There is a check-in on the main branch, which is usually the task of the QA department, where the QA department runs regression, make sure that that all the regression tests pass, and only if that happens, the check-in happens into the main branch. Usually, this the tests here consist of different levels. There are smoke tests, basic functionality that make sure that the executable is not completely broken, that you can read in a design, maybe execute some commands. Sometimes bugs are so bad that the executable crashes as soon as you type in any command, and you want to avoid that sort of thing because it means that basically development comes to a halt. Then there are
Lukas?
Yes.
One quick question. About how long do the developers' tests take to run? I mean,
well, this was kind of a sliding scale, as the company developed. became longer. So initially, there were only a few tests, and they were quick to run, and also they didn't test very much. They just tested some basic functionality, small designs, and so people tested very little before they did a submission. But as more tests were added over time, it became more and more difficult to pass that bar, and that meant that that developers would start running more regression tests of their own just to make sure that their submission had a good chance of actually passing the QA tests.
I see. But no kind of typical, if the test takes 48 hours, it's not very helpful to the developer. Or also, is there a kind of a top-down principles of coverage or minimum bar for coverage kind of philosophy or standard?
There was not a minimum bar for coverage. The tests were basically mostly based on experience and not on test coverage, but that's certainly something you could do, and that's probably a good idea to do at some point. I'll go back to that in a moment. So as time progressed, more and more tests were added and more designs were added. So at Magma, a large number of tests consisted of complete designs, basically the results of benchmark engagements that were installed as regression tests. And these often ran for a long time, like 24 hours. So because of that, it was difficult to run, and people would not run all of the tests just to speed up the process. So there was kind of a trade-off to how many tests you run when you have these big tests. So you might run only a few of the smaller designs and leave the very big ones for later. And those would be run when a release happened, but not for every overnight check-in. So there are like different gates, right? So there is a gate that has to be passed every time you check in something on the master branch, while there is a different gate for a release before you hand something to the customers. And there would be also differences between minor releases and major releases. Major releases, a major enhancement on functionality, and all of the tests would have to be run. But minor releases would sometimes be a simple bug fix or a small feature enhancement for a particular customer for a particular reason. And you could not allow the customer to wait for 3 or 4 months before the next release happens. So there would be like a special build for that customer. And in that case, only some of the tests would be run. For instance, you would make sure that the designs and libraries related to that customer would be run, but perhaps you would not run tests that were part of, that came from a different customer or had a different library. At some point, over time, the amount of tests and the length of runtime becomes quite large eventually. And so it's not always efficient to use all of the available tests. So since the main branch is protected, or the master branch is protected, developers would have to go on a side branch for different projects. And those could be short branches, just like a simple bug fix may just be a branch that has one version, that was a quick fix, and just submit it. Or it may be a feature that's more involved to develop, and this branch may exist for several months, maybe between 2 major releases, all of the changes to a particular tool, like routing or placement, would be accumulated on this particular branch and only collectively submitted at some point in the train schedule. Oops. So in all these versions.
Question, Lucas?
Yes.
Hi, this is Kareem Califala from IBM. So one thing I'm wondering about is, as you're in this branch-based development environment and you have bug fixes that may be coming in asynchronously, how do you make sure that all of the right fixes are deployed to all of the right branches in a timely fashion and you don't end up missing a fix because, I don't know, you had some development branch off to the side and you forgot to apply a critical fix to that branch? What kind of processes have you observed to reconcile all of this activity?
Okay. So I was just going to say something about that, and you can consider that, and then we'll get back to your question and see what was answered, or if you want to reformulate the question. So when you branch off from this point, from the second version on the main branch in this example, usually you develop your features based on that version. That means you don't see all the things that come in on the side here, like the features, updates, bug fixes that came into versions 3, 4, and 5. So when you actually submit your changes, there can be a conflict, and that can lead to failure because your changes on the developers branch were not compatible with some of the updates or new features or bug fixes that went into the master branch. So how do you deal with that? At Magma, that was mostly the development, the responsibility of the developers. So what people would do instead was, before submitting, they would merge in the new changes into the development branch. Of course, the same failures are going to happen, but the developer can resolve them there. Since these changes on the master branch have been checked in already, they're basically approved or golden at this point, and the developer will have to adapt to them instead of the other way around. So you can resolve conflicts here. Resolving conflict may involve changes to the code of the tool of the developer, but can also mean changes to the code of other modules that are outside of the developer's responsibility. And sometimes it can mean changes to regression tests if behavior of tools is changed in an approved manner. So then when you merge them into the master branch, you should have fewer problems. If there are no versions between 5 and 6 here, it should be identical and there should be no problems at all. Of course, creating version 4 and resolving any conflicts there takes time, so it's possible that there again have been new check-ins, but in any case there will be fewer if you do this over the course of a day than over the course of, say, 3 months. So does it answer your question, or?
Yes, it does. So I think to summarize, what you're suggesting is that pulling from upstream on a regular basis can be an effective means of propagating fixes from an accepted master branch into each of the development branches. And of course, one has to be quite disciplined about pulling from upstream or pulling from master on a regular basis, so as not to accumulate too many changes. But I think your diagram is a very nice explanation of the process. Thank you.
Yeah. So, I mean, here it's a responsibility of the developer. So the developer can determine when he pulls in the changes from the master branch, and so not be, caught off guard and be confronted with certain changes that he didn't know about, that, it comes in the morning and everything is broken. And while he was planning to do something that day, he'll have to go fix things. So here it's in a controlled fashion, and you can deal with the problems when you want, on your schedule, basically. Okay, so code coverage testing. This was not done a whole lot in any of the companies that I worked for, but some people believe in this, and there are a number of tools to test code coverage. There are different models for code coverage testing, such as function testing, statement or line coverage, branch coverage, loop coverage, variable coverage. These all are different models and might give slightly different results, but overall, it is surprising that often even with an extensive set of regressions, that code coverage is not that great. So even with a mature tool with extensive set of regressions, you might find out that only 70% of your code is covered and 30% is never executed by any of your regression tests. This is not uncommon, and code coverage is not a guarantee, really. If it's not covered, it's guaranteed not to be tested. But if it is covered, it can still contain bugs, right? I mean, just executing the code does not mean that any lurking bugs will be exposed. But still, this is a metric that people use, and there are several tools available to measure coverage. I listed a few of them here to the right. At Magma, we used pure coverage sometimes. But of course, unexecuted code is often code that's been lumped in from some other module that's unused. Like, you need like a mathematical function, and somebody imported an entire library of mathematical function, and use one of two of them, and the other 30 are unused. So you might have a matrix solver, and that's used, but finding eigenvalues is not used, inverting matrices is not used, etc. There's a whole lot of code that's not used and never tested. So this is pretty common. Other types of testing is memory testing, like memory debugger software. These kind of tools can expose potential errors, such as reading initialized memory, accessing memory that has been freed, exceeding array sizes, access outside a malloc block, memory leaks, memory that has been allocated but never freed. Potential problem. It can find potential problems in unclean code, but often even in code that has been tested and deemed reliable, if you do this sort of memory testing, you'll find a lot of problems. And these problems seemingly never seem to hurt any tests. So it's kind of peculiar in that sense. So a lot of the problems that you find here are potential problems, but may not be an actual problem. So it's a bit like lint in the sense that, you get a lot of potential errors, but they never showed up as an actual error. So some of the tools that are available for this are dmalloc, which is basically a malloc library that helps you determine whether things were not freed or whether you wrote over the bounds of a malloc block. But it does not do any checking of memory that's on the stack of a process. There's Purify Plus that works a little bit differently by instrumenting code, and it can do a little bit more, like detect uninitialized variables or detect misuse of variables on the stack, like arrays or structures on the stack. Another tool is Electric Fence. I don't know much about that one. And the various other types of testing, like performance testing, profiling, tools like gprof and Quantify to determine how much time is spent in particular functions or particular loops. And you can sometimes detect inefficient code there. So there are tools for detecting cache misses. The static verification tools like Goverity and Lint. So these are types of testing that probably should be done from time to time, but maybe not integrated in regression testing. Another type of testing is really testing inside the tool, where you can test for input sanity. For instance, when you accept a design, you can test whether it has certain properties. For instance, when you read a netlist, you want it to be free of combinational loop. You want there to be no disconnected pins. You want there to be perhaps a check for the number of logic, number of levels of logic. You may want to check for latches. Now, latches are supported by most tools, but are a frequent source of issues, timing issues, or other issues. Asynchronous logic tools are generally pretty terrible at handling asynchronous logic. And, while it's possible to create asynchronous logic, it's often a bad idea and a cause of a lot of problems. Data signals feeding into clock inputs is usually a sign of a design problem or a mistake or a problem in the constraints. Unconstrained IOs can be a problem. Bad clock latency can also cause problems at various stages in the flow, especially during CTS. Similarly, you can have library sanity checks, for instance, for unroutable pins, off-grid pins, use of M2. Using M2 in a library cell usually is often a cause of problems and generates a lot of congestion or blockages. Other things that you can check in libraries that we have found errors with is like timing sense. Doesn't match logic function. For instance, you have a AND gate, but the timing says it's an inverting timing arc from the input to the output. Well, that's not consistent. It can't really happen. It must be a bug in the library. Other problems that we found sometimes are negative slope in NLDM tables or delay models. So that if the capacitance increases, the delay decreases. That can't happen physically, but sometimes the tables do contain that sort of information. It's probably an error in the characterization, which can cause optimization algorithms to behave strangely. So now I want to move on to a regression test, and first want to distinguish a number of different types of regression tests. First are like what I call smoke tests. Basically a very simple test that makes sure that basic functionality is not completely broken. Sometimes errors, bugs can create such a severe problem that the executable is not working at all. Maybe you bring up the executable and it says like can't find init.tickle, exit, and it's gone, and you can't do anything. So those sort of tests are really necessary to not disrupt development and to protect the main branch. Then there are unit tests that test a particular component of the design. For us, that would be components like the global placer or the timer or the DDoS router that just make sure that that particular unit of the software works. Bug fix tests that were originally filed with bug reports to reproduce a particular bug can be installed as regression tests. This is somewhat time consuming and was not always done. It's kind of debatable if you want a very high level of reliability of your software, that's something you need to do, but usually there is not sufficient manpower and there's too much change in the software going on at any time to really make this pay off. Feature tests. Sometimes it's necessary to have tests that verify a particular feature that spans a large portion or the entire system. For instance, a don't touch feature, putting a don't touch on a particular cell or net means that synthesis can't change it, and basically everybody has to stay away from it and leave it alone. And basically you need to verify that that indeed happens, as there may be many algorithms that want to change that net or want to change that cell. So in that case, you would have to create a test that verifies that things that have a don't touch attribute are actually left untouched by all the algorithms. Same thing can be true for other directives like blockages or regions or things like that. Quality of results tests, or we can do quality of result testing of separate algorithms or whole designs, and I'll say more about quality of results tests later, so I just want to be brief about that right now. And then release tests. These are often extensive tests that are quite expensive to run, can create, consist of whole designs, run in excess of 24 hours per design. And so it's quite expensive to run. And that means you need like a server farm with some batch job scheduler to be able to test these all in parallel in a reasonable amount of time. So how to set up regression tests? I think regression tests should be pass-fail. And there can be detailed criteria that lead to that pass or fail. But at the top level, somebody running a regression test really needs to know whether it passed or failed, and not sort of, well, this is sort of acceptable or maybe not. There should be a uniform calling method, so that there can be a test harness in which you can install new tests, and so they can be run, hopefully in parallel, by some sort of test harness that then get us the results and reports the results back to QA. So what I propose is to base the regression tests on the exit code of the executable. Basically exit 0 means success, and exit any other number means failure. I see that some of our regression tests right now are in shell script. If we're moving to a command line interface that's TCL, I think regression tests should all be written in TCL. uniformly, and I think we need to avoid having some tests written in Perl and some in Python and some in shell script, and some in TCL, and or kind of mixes of these things where you have multiple scripts that work together to do a test, sort of unify it all into a single approach. I think TCL is probably the best choice for that. When you're in TCL, you can perhaps do a direct measurement of performance metrics. So you can use a query to determine the worst slack in the design, or a query to do total negative slack, or a query for worst congestion, things like that, and determine how they should be handled, whether that will generate a failure. One thing we had at Magma that we used in a regression test is adjustable error messages. So for instance, a global router might have a warning message at the end of the global router that says, warning, there is this much congestion left, or have this many G cell overflows, or some report like that. And you could upgrade that warning to an error, and that would result in the script failing and exiting with a non-zero exit code. So that way you could use existing warning messages to make a regression test fail. Some regression tests are based on grabbing log files. You can do that from Tickle. So there's no need to use a script from that. You can do pretty much anything that a shell script can do from Tickle. Some regression tests depend on diffing of reports, and I think you need to be careful with that and not diff things that are too large. For instance, if you diff the entire log file, it's probably going to fail all the time because of all sorts of nonsensical reasons. And even a report could contain things that change that are not really important. So diffing report is probably appropriate for a timer regression test, but may not be appropriate for QOR regression tests, where you want to leave some amount of play and have a whole set of possible solutions that are acceptable. And then finally, a fair number of regression failures will consist of crashes, segmentation violations, core dumps, things like that. And it's often difficult to determine where it would happen. So if the tool could write out a stack trace for every crash, that really helps narrow down narrow it down to what which developer needs to look at it. Another thing that can be done in regression tests that's helpful is to write out checkpoints. Basically store the design in terms of a binary or a def representation, so that it's easier to recover from that point and reproduce an error from that point without having to run the entire flow. I mean, at Magma, sometimes you had these bug reports that said, well, this thing has to run for 18 hours, and then it crashed, and go figure out why it crashed. Well, it ran for 18 hours. When they do a debuggable executable, a debug compile, it's going to run for 30 hours before it gets to the same line, and it makes it very difficult to narrow down the exact point and reproduce it. Really, you need to checkpoint the design just before the problem occurred, and then debug from that point on. Finally, we'll need a test harness of some sort that supports batch processing and cluster computing. There are several tools for that, such as LSF and Load Leveler, that farm out these batch processes in the regression tests, and then associate or compile a list of results. Any questions about anything of this? Okay. I'll move on to QOR metrics. So I think there are several types of QOR metrics. I think the important ones are the ones on this page here, which are can be grouped in timing violations, DRC violations, and user constraint violations. Timing violations, they're often measured in terms of slack, where negative slack is a constraint violation, and positive slack means meeting the constraints. The worst negative slack is a meaningful metric if you're concerned about the clock cycle. Total negative slack measures more like how many points are not meeting timing constraints, and thus is more useful if you're trying to meet your constraints by more optimization. You can have hold time slack and setup slack, and other metrics such as transition times and clock skew that can be measured. DSC violations are usually measured after detailed routing, including shorts, spacing violations, opens, VS, min area rules, antenna rules, etc. And then finally, there are user constraint violations, directives given by the user, such as don't touch, don't use, regions, blockages, things like that, that the tools will have to obey, and that may not be honored by some of the tools. Then I think there are some secondary metrics, such as power, IR drop, utilization, congestion, wire length, yes, etc. So power optimization is somewhat difficult to measure in tools. I know there's been a lot of work to determine activity of nodes in a network, but all of these measurements are somewhat inaccurate, and it's really difficult to come up with a worst case scenario for the activity in a network. Leakage power can be determined a lot more accurately. Same thing is true for IR drop and electromigration. So these tests are these are difficult to optimize in the flow, and maybe left better as outside of the regression testing. Utilization, congestions are kind of mid-flow indicators, and they may be important to track, but they're not a final result, right? Congestion kind of indicates whether you have a good chance of completing detailed route or not, but it's really not something that the final result depends on. Same thing for wire length. Then there are other metrics such as testability. For instance, cloning cells can create redundancies and can create untestable pins. That's usually not something that's measured. And then finally, there are things like runtime and memory usage, resource usage. There is a problem with interpretation of constraints. Sometimes, it's not really clear what interpretation will be given to constraints. For instance, the clock frequency, is that a hard constraint or is it merely a suggestion? Meaning that if you have a lot of positive slack, should you then move on to recover as much area, minimize power as much as possible? Or should you just, still maintain a pretty decent performance and leave a lot of positive slack? Same for negative slack. If you can't meet constraints, do you size up everything to the maximum, or do you leave things at a reasonable size level and just not meet constraints? Also, weighing off constraints against each other is sometimes not really clear how the tool is supposed to act. Should the system violate timing or meet an area constraint? If it doesn't fit in an area, should it just size down the cells until it fits, even if that means violating timing? Or should it meet timing and not fit in the area? Should the system violate min-max transition times to meet timing or power? Or should it bound min-max transition times within a narrower range and then violate timing or power? You can distinguish different, timing constraint violations by how they can be fixed. Some timing constraints violations can be fixed by slowing down the clock, while other timing violations cannot be fixed by slowing down the clock. So for instance, in most systems, a setup violation can be fixed by slowing down the clock. Now, this may be undesirable because you have a performance target to meet, but if you don't meet it, you can still run the chip at a slower clock rate, and at least it gives you the opportunity to bring up the chip and verify it and debug the hardware. Setup violations are more tricky in the sense that slowing down the clock does usually not fix, or hold time violations cannot be fixed by slowing down the clock. So hold time violations are more critical in the sense that if you have a hold time violation, it's going to be baked in the silicon, and the silicon is not going to work at any clock frequency. And that means you can't bring up the chip, you can't debug it, and you're kind of stuck with it, with a dysfunctional chip. So hold time violations are worse in that sense than setup time violations. And then finally, sometimes designers give you impossible constraints, but still expect you to do something reasonable. Sometimes they do it unconsciously, and sometimes they do it consciously. Sometimes they might just give you a 0 clock cycle just to see, what's the best you can do. And how do you respond to that? You're not going to meet the timing constraints, but are you going to do the best clock cycle, or do something that's sort of reasonable in general? So, these are kind of policy questions that need to be answered. And so in my opinion, I think it's important not to be too sensitive to timing constraints. So what are some of the challenges in quality of results testing? Challenges include stability and repeatability, interpretation of the constraints, what I just covered, size of the solution space, and correlation of metrics. So with stability, I mean that small changes in the input can cause big differences in the output. So if there is, say, a small bug fix in the Verilog that might add only a single AND gate somewhere where just one more condition was inserted in some path, that means an additional cell, and that means a buffer needs to be placed in some other location, and just ripples through the entire system. And the end result is dramatically different, with almost no single cell being placed in the same place where it used to be placed. They may be nearby, but everything is changed a little bit. And that means that everything is shaken out a little bit, and you can't really maintain much of what you learned from the previous run. Now, in addition to stability, we have repeatability, which is sort of a similar phenomenon, but it's even when the netlist is unchanged and the library is unchanged and the scripts are unchanged, it's still possible to get different results because different very small changes in the input occurred in places where you didn't expect them. And I'll say a little bit more about that in the next few slides. Then there is the size of the solution space. The number of possible solutions and the number of parameters you can tweak and the number of optimization, order of optimizations creates a very large solution space, and it's difficult to search through that entire solution space. And then finally, there is the correlation of metrics. For instance, over the process of during physical design, you have a number of metrics that kind of predict DRCs at the end, and the ability to close the routing. And those are congestion and utilization. And the question is, how well do those track, and what can be done to make them track better? Same thing is for true for timing. So the slack during synthesis, how well does it track the final timing, or timing during different stages, such as timing after placement, after global route, after optimization, after detail route, etc. How well does that track? And the problem there is that timing doesn't track that well if you don't have appropriate optimization at that stage. Okay, so back to repeatability. So multiple runs with seemingly identical inputs can result in different outputs. Why is that happening? Strictly speaking, that can't happen. But the input differences can be unexpected and unintended places, such as the username was different, the working directory was different, date and time was different, host name, host configuration, OS version were different, environment variables were different, or search paths were different. So all of these things can pull in small changes into the process that then accumulate and affect the actual optimization. So it's important to write optimization algorithms in such a way that there are no such dependencies. So a common path for divergent looks something like this. Say you have an environment variable like the current directory, pwd, and you want to store that for whatever reason. Now you allocate a string for that using str_dup. So that means that depending on what your working directory is, you're going to get a different allocation of memory here. You can have more or fewer bytes allocated. That means that subsequent allocations will be at different pointer addresses. So that now if this is in the beginning of your run, all of the nets and cells and pins all get different addresses. And that means that if there is any address-dependent logic in your optimization algorithms, then that can affect the output. Sometimes an address is used as a tiebreaker. Sometimes you sort things by address, or you hash by address. Then when you go through that sort, and maybe you have a sort of cells by address, then the order is going to be different. And if you use that order in your heuristic, optimization decisions are going to be different, which means that buffers may be inserted in different places, different cell sizes may be picked, different global routes may be chosen, and that can affect other optimization decisions, can affect timing, and then you have a divergent set of decisions from that point on. So tracking down the sources of those divergences aren't always easy. So we had to, at Magma, we would instrument the executable and trace exactly what addresses it would be at, which functions it entered at which points, and kind of do a diff and see, well, here at this function, at this point, there is a difference in the execution of the code. There's a different function called, and kind of do a diff that way and track down the source of the differences. Or you can maybe track mallocs and basically save the pointer in a log file that logs every malloc and how many bytes was done, and then diff that in different runs and see where a different amount of memory or a different pointer address is generated. So the stability problem is really something like this here, where very small changes can create a variety of results. Here in this example, in this animation, you see these bullets, or these balls, are basically dropped in the same place over the same maze, and yet they end up in different places because of tiny little differences. So small changes can have big consequences, known as the butterfly effect, and it's inherent to deterministic nonlinear systems. So it's not something that we can hope to get rid of. It's something you need to learn to live with. Examples are the weather, the stock market, fluid dynamics, and discrete optimization heuristics. So meaningless changes can affect these things, like module, file, cell, or pin order. When you reorder cells in the database, you will get a different result, even if the net list it represents is exactly the same. The cells have the same connections, same cell sizes, same everything. It's just the order in which they are visited is different. Then you'll get a totally different result. Or even things like pin names or line numbers are different. If these somehow sneak into, what do you call it, tiebreakers. And then there are, of course, actual design changes, such as inverting a single pin or moving a pad. Sometimes you might tweak the design because simulation found a bug in your netlist somewhere. You need to update the Verilog, you need to rerun everything, and you can expect to get a totally different result at that point. And this that's the result of this instability. The divergence tends to grow the more optimization you do, and the more steps, the more different types of steps you have. Discrete decisions are the biggest offenders, such as macro pad placement, buffer insertions, routing order. These things have a big impact. And smooth algorithms tend to be less unstable. For instance, global placement is kind of a numeric algorithm, tends to be a bit more predictable and a bit less unstable. Although, you know, there's no guarantee that it's completely stable. Now, so what do people do to deal with this instability? This instability is sometimes used as an optimization technique. So when you have different runs with very small differences, they can produce different results. So you can tweak some parameter or some other meaningful or meaningless change and run a number of nearly identical runs in parallel and, you know, pick the best one of it. And this is not uncommon that things are done that way. So that's a use of this instability. Another use, if you will, is changing an arbitrary parameter or a script change that causes a regression test to pass or fail. So you have a regression test that measures a quality of results metric like timing, and it's failing because of some change in code somewhere. You don't really know what's going on, what makes it fail, why the results are worse now. What you can do, and what people often will do, is shake things up a little bit and try some different parameter settings. And, you know, when you try a couple of things sort of randomly changes and one of them passes. And then you check that one in as a new regression test. This is, of course, not a real fix, but it, you know, it fixes the problem for at least there and then. Or it can be used to fix bugs. Sometimes if you have a crash, you can just change some parameter, run it again, and, you know, things happen a little bit different, and the tool doesn't crash, and you have a result. So this is all kind of undesirable behavior, but it's hard to avoid. If it's not kept in check to some extent, it can lead to organizational trashing. I've seen this happen where undisciplined changes to the code are reported as improvements, and they shake things up. And if there's not some sort of regression testing, it can make one design better. You declare it a success, you check it in, it breaks another one, you make another change, you declare it a success, you check it in, it breaks another one, and you just keep going through this cycle if you don't have some sort of methodology of catching these things. So it is a problem. So this means that it's difficult to show that a parameter setting is better without doing extensive and well-controlled experiments. The problems are somewhat similar in the medical field, where, you know, you can't really determine if a drug works by, you know, trying it on one patient. You have to do an extensive study over a longer period of time with a lot of test subjects, and then use statistical methods to determine, you know, did things on average get a little bit better or not. And you find often that making a change, you know, maybe is statistically better, but there's still a couple of cases where it gets worse, and that's something you kind of have to live with. Moreover, so you'll need a lot of data points, and also each data point is fairly expensive to get, right? Doing running a particular design with a particular set of parameters takes a couple of hours. Tweaking those parameters, you know, if you want to explore that whole space of one parameter, you need to do a bunch of runs. So it gets quickly very expensive. It's also hard to separate signal from noise this way without doing a lot of experiments. And finally, the underlying system keeps changing. So while you might be able to optimize certain parameter settings with a given set of algorithms, if algorithms change their behavior, that can change the behavior of the entire system. And whatever you learned about tweaking your parameters may be invalid. For instance, if you have global placement that optimizes wire length, your system may behave one way, then if you introduce a new version of global placement that is timing-driven placement, it may substantially change the behavior of the entire system in such a way that whatever you learned from tweaking parameters is not valid anymore, and you kind of have to start over. So what do people actually do with these problems? Well, the sort of two things that people do. One is, just do one-off experiments. Change one thing, rerun it, see if it gets better. And if it does get better, declare it a success and declare the problem solved. Now, because things are fundamentally unstable, any change has a fairly good chance of making things better. Maybe less than 50%, but it still may be 20 or 30% probability of making things better, even though it was not fundamentally a better idea. And more extensive testing would have shown that no, on average, it didn't do anything. So some of these changes are pure luck, and some of them are genuine improvements, and nobody really knows which ones are which. The other thing that people do is, yes? Okay. The other thing that people do is to tack things on at the end of the optimization in order to not disrupt the optimization up to this point. If you end up with a particular timing violation, then the tendency is to add, whatever, a buffering or a sizing step very late in the flow that attempts to disrupt very little and just fix that, one cell that has the wrong size, or this one wire that needs one buffer, and just squeeze that in without disrupting with as little as possible and as late in the flow, so as to not destabilize anything. And so the tendency is for the script to grow at the end. More and more optimizations are tacked on. Thus, every time there's one little thing that needs to be fixed, it still disturbs something else, so that needs to be fixed. And so the script tends to grow at the end, and that's kind of a problem too. But that's how people often deal with these problems. All right, so what can we say about QOR regression tests? I think it's necessary to have a number of unit tests that test only a single algorithm, such as, say, placement only or routing only. And the reason is that it's difficult to test everything in the context of a total flow, as there is, too much instability in it. So this reduces instability. Does route, say, if you test the global routing, you start with a known placement and you test to whether it can, complete the routes with a known amount of congestion or zero congestion. So that will somewhat protect the global router and make sure that the global router algorithm still works. I think these tests should use fairly simple metrics, such as, say, wire length for global placement, slack for sizing, clock skew for CTS, congestion for global routing, and not check too many parameters. As the more parameters you check, the more likely any sort of change will make the test fail. I think it's important not to diff entire log files or entire designs, as instability will almost always make these tests fail. I think tests should be exit 0 if successful, exit 1 if unsuccessful. I think blocks should be small enough to have a reasonable runtime. The most challenging designs are the biggest designs, but the runtime can become easily so large that it becomes unpractical to run these designs. But at the same time, they should be large enough to be meaningful. Maybe in the range of 5,000 to 100,000 cells, I think is a good size of cell of design to still have interesting optimization problems while running reasonably fast. And then finally, there need to be integration tests that should be somewhat challenging. At Magma and at other places, these were usually benchmark designs that were from a customer engagement that were difficult to achieve at that time. And then once they were achieved, they were checked in as a regression test so that they could be tracked. These things tend to be high maintenance. If you make them pass or fail on a particular final metric, such as slack or DSCs, if you set a tight bound, then often these tests will fail. If you set a loose bound, then you have a chance of have quality deterioration that happens kind of gradually and under the covers. So say you have a design and it finishes with 0 slack, and you allow that, it actually has a little bit of positive slack, then over time you'll see that the results are getting worse and worse until at some point it starts failing. But the contributing factors to that were already checked in a long time ago and made things a little bit worse, but not so bad that the regression test failed. And these sort of accumulate over time. So that's kind of a problem there. On the other hand, if you set the boundary very tight, they'll fail all the time, and sometimes often for reasons that aren't clear and seem unrelated to the check-ins that are happening.
Lukas, question for you. I've been quite fascinated by this discussion. My background is less in synthesis, more in timing analysis, which is hopefully maybe a little bit more deterministic. But I can appreciate all of the problems that you are describing with regards to optimization algorithms. I'm curious, is there an effort that you've seen based on your experience just to try to make optimization algorithms a little bit less, I'll say less noisy? By noisy, I mean like butterfly effects, very small changes. I know you use the extreme example of time of day or memory layout may cause large differences in results. And I think just putting testing aside, if our optimization algorithms are that unpredictable, and I was a user of a synthesis algorithm, I probably wouldn't be too happy, right?
Yeah.
I make a very small change to my input, whatever, Verilog, and I get a completely different result. Or I run a synthesis algorithm at a different time of day and I get a different result. I'm probably not going to be too happy with that. Is there an effort just to try to come up with a smoother behavior so there isn't such a high sensitivity of the optimization result to small changes in input parameters?
Yeah, there have been some efforts, but kind of limited success. So one of the things that's an improvement is these global placement algorithms, that are numeric, they're force directed, and they tend to be smoother and kind of more deterministic in the results. They're still nonlinear, so there's still a possibility of instability, but they don't tend to be as unstable as algorithms that were based, for instance, on simulated annealing, that were a lot more unstable. Another thing that can be done is sizing. So usually most libraries have sizes like 1x, 2x, 4x, and maybe 8x. So there's like a limited number of sizes. And the more sizes you have, and also, the bigger the range of sizes, the more, the smoother this can be, and the less, the less instability you get. It's still not possible to eliminate instability altogether, but behavior will be a little bit better. So yeah, those are some of the things that can be done. Another thing that's done is basically an attempt to bypass this optimization. Say you run logic synthesis once, and then if you make a small change to the netlist, say a small bug fix, you get a totally different result. That's undesirable. So what some people, do is use some sort of ECO flow where you insert the change in the final netlist of the previous run. And you can automate that to some extent. So you can kind of diff these netlists and then cut out the new part and insert it in the old final netlist. And so have a very limited amount of change that way.
Okay, thank you. A very quick follow-up, if I may, is since we're talking about testing and test metrics, is stability of output have you ever seen stability itself used as a regression metric? In other words, has there ever been a case in your experience where a new algorithm might be proposed, which maybe by random luck or whatever can produce a slightly better result, but that algorithm is rejected because it's simply not stable enough? In other words, very small changes to inputs cause large variation in output results, and therefore the team concludes we're just not going to support this. This is the behavior is too random.
Well, yes, to some extent this happens, in the QA process where, if there are a number of quality of results tests and if a number of them fail, then, the new changes will not be checked in. So it may be difficult to check in new changes, even though some of the results improved, others got worse, and there's a tendency not to check it in. So you may have to create a more statistical study that shows, well, even though some of them got worse, on average things got better, and we still think it should be checked in. But that's, more difficult case to make, and you would have to kind of go over the head of QA and make that case to management. So
okay,
it easily happens.
Okay, so by having a large enough suite of test cases, you would hope that the statistical sampling would be such that those algorithms that consistently perform better rise to the top, and those that have larger variation will probably have a tougher time being accepted. And,
yeah, I think so.
Okay, and you would have a chance of catching that just through running a large enough variety of test cases. Okay.
Yeah, to some extent, I'm not saying that the QA test suite is a large enough sample to really base that on with a high degree of confidence, but it tends to be work that way, yeah.
No. Okay, I could buy that. Thank you.
Okay, so that was my final slide. Are there any other questions? Okay, if not.
Oh, sorry.
Yes?
Sorry, Lucas.
Yes.
This is maybe not a well-formed question, but at your previous places, how important was, building everything with multiple compilers on multiple platforms and so on? I mean, given that we're kind of focused on open source distribution, which is a different world, any thoughts?
Well, I can tell you what we did there. So tools initially ran on Windows and on Linux. So those were the two platforms, and for the first about 2 years, that was the case. Then once we started engaging with customers more, Solaris was added. At that time, nearly all design houses would use Solaris internally. There was not a lot of demand for others like HP or IBM or whatever other versions of Unix. So everything was either Linux or Solaris. Linux was mostly in-house, and Solaris was what most of our customers at that time used. Then at some point, basically Windows was dropped because there was no interest in that, and it was just too different from the other two that it was more difficult to maintain. And basically the only compiler we use is GCC.
Oh, okay.
So, yeah.
Okay.
But it really was treated as a single application. So it was not a lot of variety of compilers or design executables.
Right. Because you didn't release source code, among other things. So, yeah.
Yeah, that's right.
Okay, thank you.
Okay, thanks, Lucas. That was great. It sounds like we're out of questions, so I'll stop the recording, and I'm sure we'll have a lot more discussions on this topic. A lot of what you said resonated with other companies I've been at as well.
Okay, all right, thanks.
Thank you.